Thanks a lot for the introduction, and thanks everyone for coming. This is a collaboration with Jingming Yi from Perimeter and excellent grad students who did much of the real work in this project, as well as Wei Chen Ye from Perimeter and Daniel Gottesman from Maryland. You can find the full paper through this archive number. Um, so the information in the paper is pretty diverse. So in this very brief talk, I will mostly aim to convey some of the key conceptual messages. I will start by introducing this relatively new notion of approximate quantum error correcting codes. How do we understand them, and why should we care about them? And then talk about some results that reveal the fundamental connection between quantum circuit complexity and AQEC properties. And lastly, tell you something about some interesting things that the AQEC and complexity results have to say about physics. Okay, as I probably don't need to explain too much, quantum error correction makes us believe that practical quantum computing and other technologies are possible, even in the presence of noise and errors that can easily damage the quantum systems. But beyond this original motivation of quantum error correction, it is pretty remarkable that in recent years we have gradually realized that QEC actually plays fundamental roles in various directions in physics, ranging from low to high energy in many different ways. So in this sense, QEC is not only a technological protocol, but also a fundamental language for understanding physics. Okay, so the idea for the basic scheme of quantum error correction is that you encode the logical system in a subspace of a bigger physical system. And this subspace is what we call a code. If this subspace is cleverly chosen, then it can have the ability of correcting local quantum errors. So in the study of QEC, it has been more or less customary to talk about exact quantum error correction, usually using the nice and powerful stabilizer code formalism. But the stabilizer and exact codes have a very special discrete structures. So if you consider the entire landscape of codes, they're extremely special. In particular, the codes that arise from physical systems are widely important, but almost never stabilizer codes or exact codes. So this leads us to consider more general and non-exact notions of quantum error correcting codes. As demonstrated in this map here, we have extensive understanding about stabilizer codes, but the landscape of general codes are mostly unexplored. We have some scattered knowledge, but little systematic understanding. So let me give you some more specific reasons why we want to care about AQEC codes. So first is the obvious reason. In practical scenarios, there are many things that can cause deviations from the ideal construction that you want. For example, imperfect system preparation control defects, disorder, and so on. And then from a physical perspective, codes from physical systems can have inexactness that fundamentally originates from their physics. We'll talk about this in this talk a lot. And then a specific, a particularly important specific situation is when we want codes with continuous transversal logical gates or symmetries. These are known as covariant codes. These covariant codes have been extensively studied recently, and under the name of approximate Easton-Kneel theorems. Many of these works here were presented at QIP in the last few years. And even further, for applications, it is not hard to imagine that some sufficiently small imprecision in the code is okay for practical applications. In particular, by allowing such imprecision tolerance, we can have AQEC codes that outperform the limits of exact codes in various different ways, different parameters. So this makes it appealing to study and look for general codes. And even more interestingly, we have this striking finding that an exponentially small imprecision tolerance can allow the decoding radius to approach the singleton bound. And this is in sharp contrast to the situation of exact codes, where the decoding radius is just the half of the code distance. If I'm not mistaken, we will hear about this in the next talk. And this sort of indicates that the theory of general codes might not be any sort of natural extension of exact codes. There's some fundamental distinction going on. Okay, so from now on, let's call any subspace of a big Hilbert space a quantum code. So in the basic case of qubits, we call any 2 to the k dimensional subspace of an n-qubit system a nk quantum code. Of course, not all such subspaces are non-trivial or interesting codes. So the basic question here is, how do we set the dividing line that separates non-trivial codes from trivial codes? So for example, let's consider this very naive redundant encoding where you do nothing but append a bunch of orthogonal garbage state to your logical state. And let's consider a very natural noise setting where you just simply erase a random location. Then with only probability 1/n, you're gonna erase the bad location, the location that contains logical information. So under normal measures, you actually achieve a vanishingly small code error. And this is usually the criteria in the literature when you call something a approximate code. But is this really enough? We want to rule such things out, right? Because this should not be a non-trivial code in any real sense. Okay, so to understand this thing, we introduced a AQEC code parameter called the subsystem variance, which essentially measures the amount of fluctuation or distinguishability within a connected subsystem of a certain size, controlled by this parameter d. So you can understand this d as some sort of a generalized notion of the distance, but the point here is that it is now a tunable parameter. So we can talk about the variance for different d's. For example, for this 1D chain case, if you want to compute the subsystem variance, let's say let d be 2, then what you do is you just compute the amount of fluctuation within any nearest neighbor 2-qubit size, and you take the maximum. Right. So in the literature, what's commonly used to characterize the deviation from QEC is this channel distance between the optimal QEC logical channel after the recovery and the logical identity. So here we can show that this more known quantity is indeed closely relevant to the subsystem variance code parameter. For example, under the same locality constraint, we have such kind of two-way bounds. And then let's move on to the notion of circuit complexity, which is widely important in both complexity theory and physics, but are notoriously difficult to deal with. Here we just use the very standard definition, which is the minimum number of layers of destroying local gates that generate or approximately generate the state. So here I want to highlight the difference between these two different notions of locality and circuit complexity. The non-geometric, the all-to-all case is more familiar in the CS context, and the geometric case, usually associated with some finite dimensional lattice, is more familiar in the physics context. They usually appear independently, but they're both important, and our theory will cover both. So here, let me show the simplest forms of the circuit lower bound results for the all-to-all and the finite dimensional case, respectively. Collectively, you can understand these results in the following way. On the left side, you have the condition or threshold for the code error. This delta is a robustness or smoothing parameter for the complexity definition that I forgot to properly define, but it's okay. So on the left-hand side is a condition for error, which roughly says that as long as the error is sufficiently small, asymptotically, if it scales better than the code rate, then all the states in the code subspace will be subject to corresponding circuit lower bounds on the right. So let me give some more remarks on these results. So the results reflect universal complexity features of the entire Hilbert code space, which include any superposition of the code states. So these are very important, but rarely understood, especially in physics context. And second, these error conditions are nearly optimal in various senses. And then we can actually apply these results conversely to establish lower bounds on the code error. For example, if we somehow know there is some low complexity or trivial state in the code space, this can often happen in physical scenarios, then we know that the code error of the code cannot satisfy the error condition on the left. So we have a lower bounds. Oh, let me also remark that these results work for specific NK and D parameters, but in what follows, we will mostly be concerned with code families and the asymptotic behaviors in the large N limit. So the essential idea of the proof is to adapt the Lycombe method that was briefly introduced in Anshu's tutorial on Saturday to our AQEC setup. More specifically, we need to play with the amount of fluctuation and entropy within the Lycombe. Suppose your code state is generated by some circuit of low depth, then together with the variance property, you can, if this depth is too low, then together with the variance, you can generate contradiction to the entropy of the code, which is determined by K. So in this way, you can set circuit lower bounds. The distinction of whether the circuit complexity of some state is O1 or not, or in other words, whether the state can be generated by a finite depth circuit or shallow circuit, holds particular importance in both the non-geometric and geometric scenarios. The states that have a super constant complexity are commonly considered non-trivial states. They also have other names in physics, like long-range entangled state or exotic states and so on. And our complexity results indicate such a scaling boundary for the non-trivial and trivial codes. The two typical scenarios are first when K is almost constant, then the error condition says that the variance scales roughly better than 1 over n. And when K is nearly is linear, this is the so-called good code regime, then this variance we require to be sub-constant. Then under these scalings, we will have that all the code states are non-trivial. So with these results, we can draw such very crude circuit complexity phase diagrams of codes. If you have some codes, you can just check its parameters and see which regime it falls into. So with all these general discussions, let's see some concrete examples that I think are most representative. So in this table, we collected some AQEC codes that cover different regimes of K and epsilon parameters and different code space complexity behaviors. And some of them are physically emerged, and some of them are constructed. So this demonstrates that the approximate code idea is relevant in both practical and physical scenarios. And let me note that there are many various interesting messages and insights from these different examples. So please check the paper out for more details. Okay, let's move on to the last part, which is physics. Here, let me first state a slightly informal but meaningful unifying insight, which is that you can usually find interesting codes in the low energy subspaces of many-body quantum systems with interesting physics. So in the gap case, this gives us the well-studied notion of topological order. In the gapless case, this is more relevant to the conformal field theories. So let's first talk about the gap topological order. This is a major field in condensed matter physics. A central question in this field is what features of a quantum system are associated or can serve as diagnostics for topological order. So in the community, we have these three major conditions. So the TQO condition is a strong physical condition that guarantees gap stability. Its requirement is essentially about code properties. And then we also have the long-range entanglement property, which is essentially a complexity condition, and the topological entanglement entropy condition, which is an entropic or information theoretic. So as you can see, these conditions, they are of very different nature. They are all very famous and widely useful in different situations. but there's just no very good way to talk about the relationship among them. But we find that through the lens of AQEC, we can actually compare these conditions on a relatively rigorous footing. So here, a lot of details are omitted, but very roughly speaking, the strong TQO condition that guarantees the gap stability sits on the right. It assumes that the code error, the variance, is exponentially small. But in fact, you can relax this code error to up to roughly 1/n, while still guaranteeing that the long-range entanglement and topological entanglement entropy conditions remain non-trivial. So in this sense, we have seen a clear separation between these two classes of conditions. And now let's switch gear to gapless systems, which are much less understood from code perspectives. Here we consider the low energy sectors as the code subspace where all states are CFT. So, and we call these codes CFT codes, and they are known to play important roles for our understanding of quantum gravity through the ADS-CFT correspondence. So what we first find is that, interestingly, the properties of CFT codes are determined by native features of CFT in very interesting ways. So in particular, if you analyze the subsystem variance of CFT codes, you see that they obey power law with the exponent determined by the minimum operator scaling dimension of the CFT, which is a fundamental feature of different CFTs. So this is very special or meaningful because if you just consider a randomly constructed code, it typically just have exponentially small error. So any code that has a power law error behavior signals some very interesting physics going on. And then what does the complexity side say? So one very interesting message that we found is CFTs with the property that the minimum scaling dimension is greater than the spatial dimension, and then you can see that the exponent will be greater than 1. So these states are not long-range entangled, but actually are trivial in the all-to-all sense. This is very strong and congruent with the gravity properties, including strong chaos, large central charge, and so on. So for such theories, we expect them to have very interesting things to say about quantum gravity. But very interestingly, while to our knowledge, we do not know any bounds that exclude such theories, we also do not know any non-trivial examples. And we have motivated these theories from a gravity perspective, and I'll leave this as a question here. So let me summarize some key messages that I hope to convey. So first, I hope I have convinced you that AQEC is an interesting and rich area to further explore. And we have shown that the circuit complexity and AQEC property of subspaces are closely connected to each other. And then we have shown how AQEC codes provide a powerful unifying lens for physics, and we can also get interesting codes from physics. And then this 1/n scaling is a common scaling boundary for features associated with the non-trivial order, or more generally, we propose to consider this 1/n scaling as a boundary that separates between trivial and non-trivial AQEC codes. And then a more specific one about covariant codes, the approximate async theorems put them outside the non-trivial regime. So this further strengthens the notion of incompatibility between QEC and symmetry or transversal gates, which might be of interest to many of you. Okay, so for future work, I think it will be very interesting to study this notion, called marginal order, where we mostly care about the power law error. We believe that there is rich physics to be found in this regime. And also it will be interesting to extend the theory and relative things to a more general QEC settings. And finally, I hope this work stimulates further interest into the exploration of connections between AQEC physics and physics, as well as complexity theory. Sorry. Thanks a lot.
Thanks very much. Do we have any questions? Hi, could you please go to the microphone, please?
Hi. Yeah. So, first of all, thank you for your talk. Super interesting. I was wondering, in one of your first slides, you mentioned that in some cases, the approximate quantum error correcting codes can perform better than exact ones, if I didn't get that wrong. And I was wondering, what are the features that could help you to diagnose in which cases that's going to happen? Are they noise specific? Are they application specific? Both?
Yeah, this is a great question. So I think I should describe the situation as a lot of the known examples are channel adapted. So this is one possibility, but in general, you can definitely talk about even general noise channels and still think about whether the code parameters can be better. I think this is a relatively unknown area. Yeah.
Okay. Thank
Thank
you.
you. It's a great question. Yeah.
Any more questions? So I have a quick question. Could you go back a slide, please? So when you say outside the non-trivial regime for the approximate Eastern nil theorems, do you mean that these have trivial complexity? What do you mean by outside the non-trivial regime?
So outside the non-trivial regime means that it can have non-trivial, it can have trivial states, and we do know specific examples of covariant codes that have trivial states in the code subspace. That's in the paper. Yeah.
So it means non-triviality is not necessary for such.
Yes.
Okay, thank you. Any more questions? Okay, then I'll ask one more. So you talked at the beginning of your talk about the apparent disconnect between the approximate error correcting codes and the exact error correcting codes. I'm curious what happens. Can you not somehow take the limit that the approximate error goes to 0, and what happens in that limit?
Yeah, actually, I'm not sure about this. Maybe you will get more insights after the next talk, I think.
Okay. Well, that's an excellent link to the next talk.
Yeah.